All right, so again, let's now talk about this next section, section 4.6, which is really the last section for us we're going to cover. Section 4.8 is application. So let's talk about the rank of a matrix and its relation to solution of the systems of equations. Now, before we talk about the rank of the matrix, some of the basics that we're going to we're going to put out of the way. First, we're talking about a row space and column space of a matrix. Well, the row space is simply all the rows in the matrix. So here I have let's say there's a matrix A here. So if you think of every row of this matrix as a vector, so the first row you have A sub 1, 1, 1, 2, all the way to 1n. So that first row becomes a row vector. The row vectors have only one row and then however many columns there may be. So in this case, we have first row, one row, and then n columns here. Now, the second row makes up the second row vector, the third, the fourth, and all the way up to and including the last row. This last row is the mth row. Mth row, and it goes all the way to the last column, which is the nth column. So there are m row vectors in an m by n matrix. Now, it's called the row space of a matrix because it covers the entire matrix. All of the matrix, every row participates. Now, the column vectors are simply columns, the columns of the matrix, and there you go. So this one would be the first column. Then you have the second column, and then all the way up to the last column. In this case, because there are n columns, so this would be n column. There will be n column vectors. M as in Mary. M row vectors, n like Nancy, n column vectors. So that's just terminology. And here's an example. So suppose you have a 2 by 3. There are going to be two rows. The rows are the first row, second row. So those are the row vectors. And there are going to be three columns that make up the column spaces. Okay. Now, again, in a few minutes, what we want to do is we're going to look at the relationship between the row column vectors of the coefficient matrix and solutions of systems of equations, see how they relate to each other. Now, the row space, column space of a matrix, again, just what we just went through, he just officially explains it here in our definition. A row space is a subspace of Rn. Remember, because there are n columns, right? So it's a subspace of an n-dimensional n-dimension spanned by row vectors of A. The column space is going to be a subspace of Rm, because there are m, m rows. Okay. And again, if you look at right in here, I've highlighted, there you go. That would be the column vector. Notice this is spanned by, it's a subspace of Rm because there are m rows. Okay. And let's go to our first theorem. So in this theorem, row equivalent matrices have the same row space. So once we go through, let's say Gaussian elimination or Gauss-Jordan elimination, is that going to change the row column space of a matrix? The answer is no. So if you have a matrix A and is row equivalent to another matrix B, matrix B is usually the one that is in Gaussian or Gauss-Jordan form. So if matrix A is row equivalent to matrix B, the row space of A is equal to row space of B. Okay, so that doesn't change. Now, one thing that could change, and I'll show you an example of this in a few minutes, folks. The column space may change, but the row space doesn't change. When you do like Gaussian elimination, when you do any operation that creates row equivalent matrices, the row space is intact. It doesn't change, but the column space may change. Okay. Now, let's relate this to basis. The basis for the row space. So let's say we have a matrix A that's row equivalent to matrix B. And remember, matrix B usually is in, there he has it, it's in row echelon. It could be in reduced row echelon, by the way, but the row echelon is what this theorem requires. Doesn't have to be reduced to row echelon. So this matrix B is row echelon form of matrix A. Then the non-zero row vectors of B form the basis. There you go. So if you need to find a basis for row space of a matrix, this is how it's done. And you'll see an example that follows. In this example, you have a 5 by 4 matrix. And the question simply says, find the basis for the row space. Okay, so all we got to do is change this matrix and rewrite it in echelon form. We're going to go through row equivalent matrix in echelon form. And I usually do that in Symbolab, right? And there you go. He's done the same thing probably. Now, according to this definition, the non-zero row vectors, see, those are the keywords. The non-zero row vectors of B form a basis. So check this out. Matrix B, you see the last two rows? These last two rows are zeros. These do not count towards basis. The non-zero are first row, second, and the third row. These form the basis. And he's using W sub 1, 2, and 3 to call those basis vectors. And there you have it. Basis 1, W sub 1 is 1, 3, 1, 3, first row. W sub 2 would be the second row, and W sub 3 the third row. There you have it. So it's really a very efficient, easy way to find a basis, isn't it? It's just like, how do I find the basis? This is how you find the basis. And what's interesting is that, like usually in algebra classes, well, we don't offer those anymore anyway, but many, many years ago where we did, we often work with, let's say, systems of equations, use elementary row operation and reduce them to echelon or row echelon form, reduced or row echelon form. And the solutions come out, and those independent equation actually form bases. But in algebra classes, we never talk like this. So it's interesting. Something algebraically has been done, and now we can actually see, wow, it goes just beyond solving a system, and there you go. Those are your solutions. All right, so hopefully everybody is okay on this idea of finding a basis for the row space. Again, if you have questions, please ask questions you may have. Okay, now let's go to our next theorem. So again, one last time, to find a basis for row, not column, row space. You write the matrix in row echelon. Now remember, by the way, I mentioned earlier too, bases are not unique. So what if we actually, instead of row echelon, we go to reduce row echelon? That could happen. If you go to reduce row echelon also, you can also do this. So now let's see. For this one, again, you want to find the basis for the subspace R cubed spanned by these vectors. So we want to find the basis for uh, the R3 subspace. Again, that's spanned by this. In other words, these three vectors explain every vector in that R3. Okay, so because these are rows, so you set up the matrix. Each vector is a row vector. So first, V1 is the first row, V2 second row, V3 the third row. And then you turn this into its echelon form, right? Row echelon form, not reduced, but row echelon form. And the non-zero row, there's a zero row. The third row is zero, doesn't count. What this is, the row of zeros tells me, by the way, is that the matrix A, you have three vectors. You only really need only two of these are independent. A third one could be written as a linear combination of the other two rows. That's what this matrix B, third row of zeros, tell me. So you really need just those first two rows to write every row of matrix A. And there you go. So W1, W2 form a basis for row space. Notice it's the row space of the matrix A, this one. Okay. And so there we have that one. And then what about for column space now, right? So let's see, how do we find a basis for the column space? For the column space, there are a couple of ways you can do this. The row space of a matrix A is the same as the column space of A transpose. Okay, that could be proved. The row space of matrix A is the same as column space of A transpose, and vice versa. So here he says find the basis for column space. We haven't done that. So here's how you can do this. One way, method one. So you can go column space of A, find the basis for row space of A transpose. And remember, for row space, all we got to do is just do row echelon form, look at the non-zero rows. So he does that. He transposes matrix A, which is a 5 by 4. Transpose would be a 4 by 5. And there is a transpose. And then he runs it through probably some kind of a software and comes up with this matrix in echelon form. And here's a row of zeros, which we don't need, the fourth row. So these three rows of the A transpose. Now these are bases for the row space of A transpose, for row space. If you transpose these bases, then they become a basis for the column space of A, not A transpose, but A. And there you go. So here's each of those. And then because the question was to find column space of matrix A, so next step is to actually do T transpose, transpose, and transpose of each of those. So that would be a way of doing it. To do basis for column space, do A transpose, do row echelon, get your rows, get your basis for the row space, and then transpose it, and you get the column space. That's one way. Now, the other method is also here that you can see. You can also look at, let's say for this one, where is it? So he's looking at matrix B. Okay, let's go to matrix B. That's up here. So this is matrix B. So you look at here, you have a leading one, right? This column, first column, has 1. So this would be a basis for the column vector. So you look at the ones where you have a row 1, column 1. Has to be row 1. And then you just look at that column. So 1, 0, 0, 0, 0 is a basis for column vector. And then here you have in the second row, there is a 1, second column 1. So this one also, the second column, 3, 1, 0, 0, 0, forms a basis, the other vector in the basis for column space. And you come to the third row right in here. See, there is a leading 1 in that row. And in the column below it is 0, 0. You pick that up. Notice you don't pick this column up, right? That column doesn't count because there's no leading 1. See, there's 1 in front of it. Doesn't count this column. So you have to have a 1 in the row column combination, in other words. 1 in the row and column combination, and it has to be zeros below the ones. Okay, so it looks like first, second, fourth. First column, second, fourth column forms a basis. And there you go. So you have first, second, fourth column of B. And here's a basis for the column space. Now, these are column space of A, right? So you actually pick up, there you go. So you pick up column space of A first, second, and fourth. There you go. Matrix B tells us which ones we choose out of A. So you get exactly the same column space of matrix A this way. Is everyone okay on this work? Of course, we do our own examples in a few minutes too. Now, if you're okay, then let's take a look at this theorem 15. Theorem 15 says the row column spaces have same dimension. Whatever the dimension of matrix A is the same. The row space, column space of A have the same dimension. And remember, the dimension of the matrix is the number of linearly independent rows and columns. So so in other words, it doesn't matter whether you have row space, column space, they have the same dimension. So for example, if the dimension of row space is 3, the dimension of column space would be 3 also. 3, that means you have 3 vectors, 3 rows that are linearly independent. For column space, when it's 3, that means you have 3 columns that are linearly independent of each other. All right, and let's continue on. So now we're going to talk about the rank of a matrix. Okay, so what is the rank of a matrix? Here's the definition. The dimension of the row or column. Remember, row and column space have the same dimension, so it's either or, doesn't matter. The dimension of a row space of matrix is called its rank. So again, let's say the dimension, we have an example down here. So here's matrix A, example 6, matrix A. And then B is the matrix in row echelon form, right? Matrix B. Now, there are 3 independent rows here. See, I don't have a last row of zeros. So I actually have 3 independent rows. So the rank of this matrix is 3. So they call this a full rank matrix. If the rank, the number for the rank is the same as the number of rows in the matrix, then that matrix, they call it a full, quote unquote, full rank matrix. And the rank of a matrix later on, we see it ties in with the inverse of the matrix also. So the matrices that are full rank end up having inverses. If a matrix is less than full rank, then the inverse will not exist. This is coming up later on. We'll see this coming up. Okay. And remember, how do we determine the rank? Get the matrix in its row echelon form. That's all you got to do. Row echelon form, and you count the number of non-zero rows. Non-zero rows. So here I have 3 non-zero rows. Therefore, this is a full rank 3. Not the columns, number of rows. Okay. And by the way, this thing, let's see, this is a rank 3. So the dimension of the column space, see the column space, now you have 4 vectors in the column. The column space of this will also be 3. Right? Here's the column space. Remember? First column. So it's going to be 1, 2, 0. The second column, that's second row leading 1 is second row is 1, and in the second column. So the second column of matrix A forms a basis. And there you go. The third one does too. So the dimension of row and column space are both 3 in this case. The 1, 1, negative 3 doesn't count because it doesn't have a leading 1. You see that? That's 3. The leading 1 is here. And that was picked up in that third column. All right, another definition. Let's talk about the null space now. The null space of a matrix. Now, the null space here is simply the number of the dimension, the number of solutions to the homogeneous system. Okay, now let's look at the solution of a homogeneous system. Remember, that's when we have AX equal to 0. Must be 0 on this side, on the right side. It has to be 0. That's called a homogeneous system. Now, the set of all solutions of the homogeneous system is called the null space. That's what it's called. The null space. And N for null space, NA. That's the notation for the null space of A. And this just tells you the number of solutions to coefficient matrix A here, which is part of this system of equations. Now, the dimension of the null space is called the nullity. The nullity, by the way, also some other textbooks call it the kernel. Kernel with a K. Kernel. The kernel of a matrix. So we talk interchangeably, the nullity or the kernel of A. Okay. Now, the nullity, the nullity here, this nullity also tells us the number of free variables in solution to this system. The number of free variables. I'll give you example again in a few minutes here. Now, just a couple of notes about nullity here. If the nullity is positive, remember, nullity therefore is the set of solutions of a homogeneous system. So it could be like 0, it could be 1, 2, whatever. If the nullity is positive, like maybe 1, maybe 2, 3, whatever, there are infinitely many solutions if the nullity is positive. That means some variables can be freely chosen. Remember parametric solution to the system? Those have nullities that are greater than 0. If the nullity is 0, that means the system has only one solution. Remember, nullity is a number of solutions. If nullity is 0, means this homogeneous system has only one solution, and the solution is the trivial solution. Everything has to be zero, in other words. That's the only solution. That's what nullity zero means. Okay. So again, nullity zero means you only have trivial solutions. Nullity other than zero, positive, any positive number, that means you have infinitely many solutions. Okay, so that's what the nullity is. Probably said too much about it. Okay, now here is an example, finding the null space. And again, we will do our own examples too, folks, in a few minutes. This one says find the null space of a matrix. So here's a matrix, right? Remember, the null space is a number of solutions to the homogeneous system. So that means we need to solve this homogeneous system, right? AX equals 0. So we can go to Symbol Lab and run this, and this is what we're going to get. Notice there is a third row of zeros in this matrix that is in echelon form, right? So he actually goes, in this one, he goes to reduce row echelon. Why? Because he's actually solving the system. Remember, we want to solve and find the number of solutions. So he goes all the way down to reduce row echelon. And there you go. The first row is here. The second row is there. X1, X2, X3, X4. And the second row, X1, 0, X1, 0, X2, plus X3, plus X4. Okay. Now, there you go. You see the X2, X4 here are free variables. So this is one that has nullity that's positive. The nullity of this is positive, of this matrix, of this system. Okay. And I'll show you how to find the nullity. So this is just to show you that you can write the system in parametric form. And we have two free variables, right? Two free variables. So that means the nullity of this is 2. The null space is 2. Because we have two free variables. Okay, and here's a solution, by the way, to the system in parametric form. A basis would be this column vector, -2, 1, 0, 0 forms a basis. -3, 0, -1, 1 forms another basis. And there you have that one. So we have two bases here, right? So how many solutions? We have two vectors, right? So this one, the nullity is 2. Okay. And the null space, what was the question? Find the null space. There you go. This would be the null space. You have two vectors in it. Any questions about this example on finding the null space? So to find the null space, pretty much all you gotta do is solve the homogeneous system. That's it. Find the homogeneous system, and there you go. If the solution to this, by the way, if this system had only trivial solutions, its nullity would be 0. Okay. Now, let's see. Theorem 17. This one, dimension of the solution space. So suppose we have a matrix of coefficients here of rank R. The dimension of the solution space is n minus R, where here R again is the rank of the matrix, and then the nullity is n minus R. You see that? The dimension of solution space. That's called the nullity. So n is rank plus nullity. So you can find nullity by subtracting the rank from n. That gives us the nullity. So here's an example again, folks. So here's a matrix. Write it in its reduced row echelon form because we want to solve the system. Now, here n is 5, right? We got 1, 2, 3, 4, 5 variables in here, right? There are 5 variables in here. So n is 5. What is the rank of this matrix? The rank is going to be the number of it will be the non-zero rows of the matrix, right? Matrix B, the fourth row is all zeros. So it has 1, 2, 3 non-zero rows. That's the rank of matrix A. So if you subtract the rank from the number of variables, 2, that would be the nullity. The nullity is 2. Okay. It says find the rank and nullity. Everyone okay on how we do this one then? The rank you get from the matrix in reduced echelon form. The number of non-zero rows. That would be the rank. 3. First row, second, third row. N is the number of variables. N minus rank gives you nullity. Okay. And in part B, it says find a subset of column vectors that form a basis for column space. And again, for that one, remember you look at a row with leading 1, a row with leading 1, a row with leading 1. True? And then, so first row, in the first row, first column, there is a leading 1. So the first column is a basis for column space. The first column of A, so reflected back to A. There you go. So here's one basis right there. And then look at the leading 1 in the second row. This means the second column. The second column of matrix A forms another basis. That's A2. And this column 3 doesn't count. True? Because there is no leading 1 there. It's a 0. So we don't look at this column. Let's look at only the rows with leading 1s. Only the rows with leading 1s. Those columns count. So here's a leading 1 in the third row. So column 4 is in matrix A is this one. That forms another basis. So there you have a basis for the column space. Again, what does this mean? That means I have 1, 2, 3, 4, 5 columns, right? There are 5 columns of matrix A. Only 3 of those columns are independent. The other 2 columns can be written as a linear combination of A1, A2, and A4. That would be column 3 and column 5. So that's all that means. Again, any questions, ladies and gentlemen, so far? No questions? Okay. If no questions, then let's continue on. And we are almost nearing the end here, folks, and then I'll give you some examples. And this one, a solution of system of linear equations. And there you have, again, we are almost nearing the end. Almost. Now, for this one, if you actually look at here, the theorem, you have x equals x sub p plus x sub h. what this theorem says is the following. Suppose you have a particular solution for the non-homogeneous system AX equals B. Then every solution of the system is written in the form of the sum of a particular solution plus a solution for the homogeneous system. That's what X sub H is. Now, this form of expressing the answer, by the way, also in in differential equation classes, that's how they do. That's how they write their answers too. Whenever, if you're taking either now or later differential equation, this looks familiar to you. But anyway, for now, for this course, remember we have a solution to homogeneous system AX equals A, and we have a solution, a particular solution for AX equal B. So if you combine them together, then you get what we call the general solution. That's what X is. Okay. So in this example, it says find the solution for the non-homogeneous system. So we're going to write the system like this: 4 variables and constants. So this matrix is going to have 5 columns. And then you do Gauss. Let's see here. He hasn't done Gauss-Jordan. It just does Gaussian. It's in row echelon. Well, actually, it is in reduced row echelon form here. See, we have the third row of zeros. So that means the rank of this matrix is 2. You have 2 non-zero rows. Rank is 2. And therefore, the solution can be written in parametric form. And we have some free variables here, right? Remember, the first column is x sub 1, second is x sub 2, third x sub 3, fourth x sub 4. So we're going to let x sub 4 be t, x sub 3 be s. So there are 2 free variables here. 2 free variables. And the solution to the non-homogeneous system, AX equals B. Remember, 5, 8, 9, negative 9, that's your B. It's going to be this. So the solution to the system, is going to be 2s minus t plus 5, negative s plus 3t minus 7, and x sub 3 would be s 0t plus 0. And then you can rewrite these as 3 column vectors, right? Separate first column for s. You get 2, negative 1, 1, 0. There you go. The t column would be negative 1, 3, 0, 1. There. And the constants that don't have t, the constants would be 5, negative 7, 0, 0. This would be the solution. This would be the particular solution. Okay. And so there you have it, the particular solution. And the solution to the homogeneous system is going to be these 2. Combined together, that form the solution to the system. Set of all solution vectors of the system. And there you have that one. Again, we'll do our own examples in just a moment, folks. Let's see, number 14, theorem 14 here. solution of system of equation. The system AX equal B is consistent if and only if B is the matrix of constants. For this to be consistent, for this system to be consistent, B must be in the column space of A. What does that mean? You can see down here. When you write AX, we can write AX other than a matrix A times a column vector of variables. We can write them in this form, the form of column vectors. For each column, you have a vector. So we can write them this way. So this matrix B must be in the column space of matrix A in one of these columns. It has to be in that. So let's say for this one now, let's see if this system is consistent. Well, so A is the matrix of coefficients, B is the matrix of constants to the other side of equal sign. Okay, so put them together. The augmented matrix looks like this, right? And you go to the reduced echelon form, Gauss-Jordan. And again, because we have 3 unknowns and only 2 independent equations, the rank of this matrix is 2 because it has 2 independent linear equations. So that means we have 1 free variable, right? And B, which is -131, it says this is in the column space of A, therefore the system is consistent. Now, how is that in the column space of A? Let's see, what is the column space of A? It's going to be the first column, 1, 1, 3, and the second column, 1, 0, 2, right? So this, again, this just shows that B is in the column space of A. The -1, 3, this. Again, the column space of A is just 1, 0, 0 means first column. And column space here is the second column, this one. Those two make a basis, right? Because they're bases for the column space. And remember, that means every other column is a linear combination of only column 1, column 2. So that's how we know this is consistent. That third, even this third column is in this space. You can write -1, 1, -1 as a combination, linear combination of column 1, column 2. And you can write the last column, which is matrix B, as a linear combination of 1 and 2. And that's what we wanted to show. And that's what this says. AXB is consistent if B is in the column space of A. And we showed that. And I think this is the last thing about this section. We had summary of equivalent conditions before, right? This one, we've seen these before. So as we go through, we keep adding to this. So for example, all of these conditions mean the same thing. When we say A is invertible, that means the system AX equal B has a unique solution. That means AX equals 0. The homogeneous system has only trivial solution. That means A is row equivalent to identity matrix. When you do Gauss-Jordan, you get one kind of like 1, 0, 0, 0, 1, 0, 0, 0, 1. That's what you're going to get. That means the determinant is not 0. That means the rank of a matrix is n. It's a full rank. Now we can connect it to the rank. So numbers 6, 7, and 8 are new for us. And that means the n rows are linearly independent. If the rank is n, means it's full rank. That means you have n rows that are linearly independent, and n column vectors are linearly independent. So there you have it. We covered a lot of ground, a lot of terminologies, right? It's like, now how do I work with this, right? So let's take a look at some examples here. I promise you we work some examples, but let me ask you this: Well, I was going to say let's take a break, but we still got 10 minutes, so let's do this. Let's actually look at some examples. Now I'm going to switch to my notepad here. Let me change my share. And again, hopefully everybody's okay. If you have questions, please ask, folks. Otherwise, I really think you're okay. Let's switch to the notepad here. And we're gonna try some examples. Okay. So let's see what example. Oh, one thing I mentioned earlier, to give you an example, I mentioned that elementary row operations don't change the row space, but they may change the column space, right, of the matrix. So here's an example of that. So let's say my matrix A is 1, 2, 3, 6. Okay. Now, you can see the second column is a constant multiple of the first column, right? 3, 6. So 3 times 1 gives you 3, 3 times 2 gives you 6. Okay, so the column space is just going to be a constant multiple C times 1, 2, right? So it's just 1, 2. Now here's matrix B. Matrix B, I have 1, 3, 0, 0. Okay, it's the same matrix I had. This time I'm thinking in terms of the rows. You double up on the first row, you get 1 times 2 is 2, 3 times 2 is 6. Once I do elementary row operation, I can reduce this matrix, right? So what is the column space of matrix B? The column space of this matrix is just going to be 1, 0, right? A 1, 0, or a constant multiple of 1, 0. There you go. You see, you have 1, 2, you have 1, 0 here, and that's what we mean. The column space changes when we do elementary row operation. Matrix B is matrix A, where I did the elementary row operation. So again, here, this is what I meant. The column space could change, but the row space doesn't change. Okay. Now, let's take a look at another example here. This next example. So for this one now, suppose I have this matrix. Okay, so my matrix is going to be 1, 2, 0, 2. Then I have 3, 6, 0, 6, -2, -5, 5, 0, 0, -2, 10, 8, 2, 4, 0, 4, 0, -3, 15, and 18. This is a large system. In fact, I have 4 equations and I have 6 unknowns here. 1, 2, 3, 4, 5, 6. So my x vector is going to be x1, 2, 3, 4, x up 5, and x up 6. So there's my matrix of variables. And this should equal to, let's say I'm solving a homogeneous system there. That's my homogeneous system. And matrix B, this is for the non-homogeneous system now. Suppose B is 0, 0, -1, 5, and 6. So in other words, here I'm thinking AX equals 0, homogeneous system, AX equals B, the non-homogeneous system. Okay, now when we solve this one for the homogeneous system, equals 0. And we can go to a symbol lab to do this. Okay, I've done it. Well, let me show you what I got from symbol lab. I got 1, 0, 0, 0. And you're welcome to try this out also as I'm writing this. And then for the second column, I got 3, 0, 0, 0, 1, 0, 0, 4, 2, 0, 0. And fifth column was 2, and then they're all zeros. And the sixth column was 0, 0, 1, 0. So this was the solution to the homogeneous system. Now, the solution to homogeneous system. Remember, these are the coefficients on x1, x2, 3, 4, 5, and 6. Well, the last row is all zeros, so I don't get anything out of this one. The row before that, remember, this is the coefficient on x6. So from the third row, that means x sub 6 is 0, correct? So we got one of the values, x sub 6 is 0. Now look back at previous row, second row now. Let me put these x1, x2, x3, x sub 4, sub 5, x sub 6. Okay, now in the second row here, x sub 5, see, notice there's nothing with x sub 5, 0 x sub 5. So I can let x sub 5 be my free variable. I'm going to let x sub 5 be t. Okay. And x sub 4, I'm going to let that be my other free variables. X sub 4 is s. Now I can write x sub 3. Isn't x sub 3 equals, move 2 to the other side. Remember, there's this imaginary dotted line and then 0, 0, 0 here for the homogeneous system. So x sub 3 is going to be moved this to the other side of equal sign. It's -2 x sub 4, right? X sub 3, -2 x sub 4. But then x sub 4 was my free variable, s. So that's -2s. Okay, -2s. Let's go to the first row. In the first row, how do I write the first row now? So x sub 6 is 0, right? And I can write x sub 1 is x sub 2 here. X sub 2, see, I don't have any x sub 2 here. So I'm going to let x sub 2 be my other free variable. I'm going to let x sub 2 be r. Okay. So I can write now x sub 1 in terms of these other variables. Move each of these to the other side of equal sign. Each of these. And we're going to get x sub 1 is 3 on the other side becomes -3. X sub 2 is r. So it's -3r. Move 4, x sub 4. 4 to the other side becomes -4 x sub 4. That's -4s. And move 2 x sub 5 to the other side becomes -2 x sub 5, which is t, -2t. And there we have that. So what does, well, let's keep this for what it is. I solve for x sub 1, 2, 3, 4, 5, x sub 6, 0. Now, for the non-homogeneous system, let's look at the non-homogeneous. The non-homogeneous system, when I did Gauss-Jordan on that one, and remember, non-homogeneous was this one. You have 1, 2, 3, 4, 5, these 6 columns, and then now you have a 7th column, this one. So if you do this in Symbolab, you actually have to do a 4 by 7 matrix. 4 rows, 7 columns. And this time, you put 0, -1, 5, 6 there. So here's what I got for the non-homogeneous system. And this was again Gauss-Jordan on the first one I did with Symbolab. And this is Gauss-Jordan for the second one. So for the non-homogeneous system, I got 1, 0, 0, 0. And then I got 3. Now compare this, by the way, to the one directly above it. This is, remember, for non-homogeneous. And then I got 0, 1, 0, 0. Isn't that cool? The next column turned out to be 4, 2, 0, 0. The next column was 2, 0, 0. Looks exactly the same, doesn't it? And the last column was 0, 0, 1, 0. And I got the 7th column was 0, 0. And then it was 1/3 and 0. There you have it. So this portion, the first 6 columns, indeed look identical to the homogeneous system. Okay, now let's write the solution for the non-homogeneous system, and let's see how it's going to fare compared to homogeneous system. Just like the homogeneous counterpart, this last row doesn't do anything for me. Now remember, coefficients on the columns are column 1, x1, x2, x3, 4, 5, 6. So x sub 6 from the third row, x sub 6 is 1/3. Remember, for homogeneous system, x sub 6 was 0. Now it's 1/3. Now, the rest of it is pretty much like the other one. X sub 5 would be my free variable. X sub 4 would be my other free variable. X sub 3 would be -2s. X sub 2 would be r. It's exactly the same as what we did up here. And x sub 1 is going to be -3r, -4s, minus 2t. So notice again, the solutions look almost identical. The only difference is x sub 6. So let's finish this off. Therefore, the solution to x sub 1, x sub 2, x sub 3, 4, 5, 6 is going to be -3r, -4s, minus 2t. And then I have r, that's x sub 2. X sub 2r, x sub 3 is -2s. And s, and then t, and 1/6, right? I'm sorry, 1/3, 1/3 right here. X sub 6 is 1/3. X sub 6 is 1/3. Right? That's the solution to the non-homogeneous system. Now, here's the cool part, folks. Look at this. I can write this as R. I'm looking at just the first columns, the first numbers that have R in them, like -3r, 1r. The third row doesn't have an R, so that's 0r. This one has 0r, 0r, and 0r, right? There's no R's other than the first 2 rows. So R times -3, 1, and it's 0 elsewhere, right? I got -3, 1, and then I gotta have 4 zeros here. Okay, and then we're going to add T, well, RST. Let's go alphabetical. RS. Look at S. The coefficient on S in the first row is -4. There is no S in the second one, so that's 0. -2, S is 1. T has no S, and the 1/3 has no S, 0. Okay, so those are the coefficients on S. Let's write the coefficients on T. First row has -2T. That's -2. There is no T in the second row, no T in the third, no T in the fourth. There's one T in the fifth, and 6, there is no T. There you have that. These are the solutions to the homogeneous system, right? Look at this one. These are the solution to homogeneous systems, exactly. The only thing that I add to the solution to homogeneous system is 0, 0, 0, 0, 0, 1/3. And this would be particular solution. Okay, so notice the entire system, therefore, the solution to the system AX equals B, the non-homogeneous, can be written as the sum of the ones that belong to the homogeneous plus the particular solution. Now, the ones that belong to the homogeneous, the column vectors that belong to the homogeneous system, first, second, third, these form the basis. So these are the bases for matrix A. Those are the bases. The bases come from the homogeneous system. Okay, so there is the example here. Okay, any question about this examples, ladies and gentlemen? We have come to our break time, so let me actually let me pause the recording if I can find out where I am. Okay, so let's take a look at our next example here. In this next example, we're gonna look at the following. Let's take a look at this. Mhm. Okay, so in this next example, let's say the question is we want to find a basis. Okay, let's find a basis for the null space of a matrix, for the null space of matrix M. Okay. Space of matrix M. Okay, or A, doesn't matter. Okay, so the matrix M here is going to be, let's say it's 1, 2, 0, 2, 3, 6, 0, 6, -2, -5, 5, 0, 0, -2, 10, 8, 2, 4, 0, 4, 0, -3, 15, and 18. Okay, now this matrix is actually the matrix from my previous example, right? That should be familiar. Okay, so that's the one we did before the break. In other words, here, let me show you what I mean. There you go. It's the same matrix, this matrix right here. So this time you want to find a basis for the null space of that matrix M. So the null space, let me write that. The null space of matrix M, and call it N of matrix M. is the solution space of the homogeneous system, right? Now, our homogeneous system, again, just before the break, when we solve this, here's our homogeneous system, right? And by the way, since I have this on here, when I look at the Gauss-Jordan here, let's see, the rank of this matrix, the number of independent rows, I don't count the last row because it's a row of 0. The rank is 3. And how many variables were there in here? I had 1, 2, 3, 4, 5, 6 variables, right? So n was 6, the number of variables. Therefore, what's the nullity? Remember, the nullity is going to be n minus r. It's going to be 6 minus 3 or 3. The nullity is 3. What does that mean? It means exactly this. You have 3 solutions to the homogeneous system. So that's what nullity is the number of solutions in the solution space for the homogeneous system. Okay. Now, so the vectors that I found, I'm now copying the vectors that I just pointed out to you. Remember? Let me show you one more time. Here's one vector, -3, 1, and then 4 zeros, then -4, 0, -2, 1, 0, 0, and the last one. So there you go. So my first vector in the null space is -3, 1, and then 1, 2, 3, 4 zeros. Okay. V2 is going to be -4, 0, -2, and then 1, 0, 0. And V3 is going to be -2. Then it ended up being 3 zeros, a 1, and a 0. And there you have it. This is what's called the null space. So hopefully I'm clarifying some of these jargons that we just went through for the last hour, hour and a half. And there you go. Hopefully everybody understands now what we mean by null space. Null space is simply the number of solutions in the solution space of the homogeneous system. Okay. Now, for this next one, let's say our next example is this. Find a basis, find a basis for column space of matrix, whatever, M, A, doesn't matter, of matrix M. So suppose this is now my matrix M, which is in echelon form. Okay, so it's going to be 1, 0, 0, -2, 1, 0, 0, 5, 3, 0, 0, 0, 0, 1, 0, 3, 0, 0, 0. So suppose this is a matrix that's in echelon form. The basis for column space. Remember how that worked? Let me get my highlighter. So we're going to look at, for this, we're going to look at the rows with the leading coefficient of 1. So it's this one, and this one, right? Those are the leading coefficients. The leading coefficient is 1. So for column space, you're going to look at the column where these ones occur. Notice I don't pick up this third column because that doesn't have a leading 1. It's a 0. Okay, therefore, the basis for column space, and I'll call it C1 for the first one. First one is going to be 1, 0, 0, 0. And then the second column space, C2, that's going to be -2, 1, 0, 0, and C4, right? C4 is going to be 0, 0, 1, 0. That's the basis for the column space of this matrix. Okay. Now, just again to show you what this means. That means I have 3 independent columns. The other 2 columns are linear combination of these 3. So let me show you this. So note, let's say I want to see what linear combination of C1, C2, C4 gives me the third column, 5, 3, 0, 0, right? Because that's what this means. I should be able to write column 3 and column 5 separately as a linear combination of these. So that means a linear combination, because I use C for those, I'm going to use K for the constant. K1 times 1, 0, 0, 0 plus some scalar multiple of the second column space and some scalar multiple of the last column space. All right. Now, if I work this, remember, this can be equal. For example, the first element of this on the left, I have 4 by 1 matrix. The first element is 5. To be equal to the right side, 1k1 plus negative 2k2 plus 0k3 should equal 5, right? So I'm going to write these now. So k1, that's 1k1, negative 2k2, 0k3 is just that equals 5. And 3, how can I get 3? Well, 0k1, I'm going to skip that. 1k2, that's just k2. And 0k3, there, k2 must be 3. If k2 is 3, back substitute, and from this, k1 must be what? 11, right? Because 3 times 2 is 6, negative 6, add 6 to both sides. K1 is 11, K2 is 3, and 0K1, 0K2, 1K3 equals 0. There you go. The system is solved. So that's what it means. So I can write 5, 3, 0, 0. This can be written as the following linear combination. K1, 11 times the first basis, 1, 2, 3 zeros, plus K2 was 3. 3 times the second basis, negative 2, 1, 0, 0, plus K3 was 0. 0 times, in other words, we don't need the third column. The 2 columns will take care of this one. And you can see 11 plus 3 times 2 is negative 6. 11 and 6, negative 6 makes 5. 11 times, these are all zeros. 3 times 1, 3. Then Z has all zeros. And this was 0. K3 is 0. So there you go. Just want to again clarify, what does this mean when we just say the column space? Column space is the number of independent columns in the matrix. Now, what does the row space looks like? The row space here, let's do our row space for that matrix. The row space is going to be, again, just the rows with the leading one, right? So here's my first basis vector. It's going to be first row, 1, negative 2, 5, 0, 3. True. The second row, the second vector, the basis is 0, 1, 3, 0, 0. Right? That's the second row. And the third row, be 3. The third row is going to be 0, 0, 0, 1, 0. There. These are the row space, and those are the column spaces. With the row space, again, these span the matrix. Okay, so hopefully everybody's okay on this example. Let's see. Now, let's do another example here. In this next example, let me do this for this next example. This would be like our fourth example, I think. I'm going to let the matrix of coefficients be negative 1, 1, 2, 3, 2, 1, 2, negative 3, negative 2, and the variables are x1, x2, x3. And suppose my non-homogeneous system, the system is equal to that. And this is what B is, by the way. So you're looking at the form AX equals B, the non-homogeneous system. So for this one, what are we doing? Pretty much what the book asked us to do. With that one last example we did in the book, we want to show B is in the column space of A. Okay. So in other words, what we want to say is this. If B is in the column space of A, that means we can write this vector B as a linear combination of the columns. That's what that means. Okay. So for this one, when you solve this one, okay, when I did Gauss-Jordan on this system, the solution turns out to be x1 is 2. You can verify this, x2 negative 1 and x3 is 3. Okay, that turned out to be the solution. And you can see negative 1 times 2 is negative 2. 3 times negative 1 is negative 3. Negative 2 and negative 3 so far add to negative 5. 2 times 3 is 6. 6 minus 5 is 1. See, there you go. This is a solution to the whole system. I did in Symbolab, I actually put 1, 2, 3, 4 columns in Symbolab, and I got that solution. Now, to show that B is in the column space of A, you go x1 is 2. 2 times the first column, negative 1, 1, 2. x2 is negative 1, minus 1 times the second column, 3, 2, 1. And plus x sub 3 is 3. It's going to be 3 times. The third column is 2, 3, negative 3, negative 2. You see that? When you do this, 2 times negative 1 is negative 2. Minus 3, negative 5. 3 and 2, 6. Those add up to 1. 2 times 1 is 2. Negative 1 by 2 is 2. Those add to 0. 3 times negative 3 is negative 9. And the last row, 2 by 2, 4, minus 1 is positive 3, minus positive 3 minus 6 is negative 3. And there you go. You see how that worked? B is in the column space of A, means we can write B as a linear combination of these columns. And in case you wondered, let me put my Gauss-Jordan. I never wrote what that one was for this. How did I get this? Gauss-Jordan looked like this. I got 1, 0, 0, 0, 1, 0, 0, 0, 1. And I got 2, negative 1, 3. That's how the solution x sub 3 is 3, x sub 2, negative 1, x sub 1 is 2. Okay. Notice that matrix A coefficients, this matrix, let me put that as a notice, that matrix A is row equivalent to an I3 identity matrix of size 3. And that was one of those 10 things that we just saw before the break. Not the 10 things in section 4.2, by the way. The one that said all of these statements means the same thing. determinant of A. A is invertible, means determinant is not zero. It means A is row equivalent to n. That's the one. Now, for this one, the other thing that said was determinant is not zero. I calculated the determinant, turned out to be -17, not zero. So that checks also. That was one of those things. Again, the equivalent statement. A will be invertible. I didn't find the inverse. Now, for this one, let's do nullity. Let's do nullity of A. Nullity of A is going to be, in this case, number of columns of A, right? 1, 2, 3, right? It's n minus rank of A, right? Remember, n is the number of variables, which will be, because matrix of coefficients has as many columns as there are variables, right? So that's why n is the number of columns in the matrix of coefficients. So that's 3. What's the rank of this matrix? Well, if you look at the solution, this is a full rank. You have 1, 1, 1. So you have 3 rows. I don't have a row of zeros. So the rank is 3. This is a full rank matrix. And it's full rank, that means it has an inverse. So the nullity is 0. There you go. And that's what the nullity is. Okay. Now, this is the only solution, right, that it has. That's the only solution it has. So if the nullity is 0, remember, so if you write the general solution, remember general solution is particular solution plus the solution to the homogeneous system, right? Nullity is 0. Nullity is 0 here. That means the solution, because XP has 3, right? It has 3 solutions. So because nullity is 0, this means AX equals 0 has trivial solutions only. In other words, the solution is this: x1, x2, x3 equals 0. So your solution is particular solution, x1, 2, 3, which is 2, -1, 3, plus the homogeneous 0, 0, 0. So the solution is really just 2, -1, 3. And there you go. Okay, so hopefully, again, I'm trying to put in context all of these jargons, terminologies that we just talked about. All right, so there we have this example done. Now, let me see, how about, let's do another example. And this next example, put that away. In this next example, let's say we want to find a basis again, okay, for the column space of a matrix. So here's our next example. Find the basis for the column space of matrix A. Now, here's my matrix A. This matrix A is 1, 2, 2, -1, -3, -6, -6, 3. Then I have 4, 9, 9, -4. Let's do -2, -1, -1, 2, 5, 8, 9, -5. And finally, 4, 2, 7, -4. It's a large matrix, but then again, if I'm using Symbolab, why not? So this is a 4 by 6, right? So what do I need to do now? I need to write this matrix in its row echelon form. Okay, so there you go. You're going to transform this in its row echelon form. And again, I should confess, I use Symbolab, okay? I'm not crazy to do this by hand. Okay, so here's what the row echelon form looks like. I get 1, 0, 0, then negative 3, 0, 0, 0, 4, 1, 0, 0, negative 2, 3, 0, 0, 5, negative 2, 1, 0, 4, negative 6, 5, 0. Okay, so there you have it. This is the row equivalent matrix, right? Row echelon form. Now, so for this one, if we can find a set of column vectors of R that form a basis for the column space of, and this is what I'm calling R, by the way. There you go. So if I can find, again, a set of column vectors of R that form a basis for column space of R, then the corresponding column vectors of A corresponding to these will form a basis for the column space of A. See what we're doing? Again, I'm finding the column space of R, whichever they are, which I will do in a moment. Remember, the column space is the one that has a leading one and zeros below it. There. It has 1 and 0 below it. So if I can find, again, a basis for column space of this matrix, it will be exactly the same basis for the column space of matrix A. We want to find it for A. So first column, third column, fifth column, first, third, fifth columns of R, those that are containing leading ones of the row vectors, okay? So C1, let's say prime. I'm saying prime because it's for the R matrix. It's going to be 1, 0, 0, 0. And C3 prime, that's going to be 4, 1, 0, 0. And finally, fifth column of R, which is 5, negative 2, 1, 0. These form a basis for column space of R, right? This is for column space of R, right? Now, again, the corresponding column vectors of A are going to be, call it, oh, I'm doing column. For rows, I use V like the book does. For columns, I use C. I think the book may use whatever, B or something like A, doesn't matter. So there you go. Now, first column in A, that's 1, 2, 2, negative 1. And then the third column, see, this is a corresponding column, is 4, 9, 9, negative 4. And the fifth column is going to be 5, 8, 9, negative 5. And there you have that one. These form a basis for the column space of A. And that's what we wanted to do. What about, let's say we want to do a basis for the row space. Find a basis for the row space. So to find the basis for the row space, now you look at just the ones that have leading ones. Let's say W1. That's going to be the first row. 1, negative 3, 4, negative 2, 5, 4. W2 is going to be 0, 0, 1, 3, negative 2, negative 6. That's the second row of this matrix. And the third row, we got 0, 0, 0, 0, 1, 5. right? 0, 0, 0, 0, 1, 5. And that's W3. Notice the row space, the column space have exactly the same number of vectors. And that's what one of the theorems said, that the dimension of these would be the same, right? Okay. And again, any questions, if you have any questions, please ask. Otherwise, I just assume that you're okay. Does anyone have any questions so far about these examples? No? Okay. Um, let's see. Let's take a look at, if no questions, then let's go to these exercises. Let me look in the chat in case following along. All right. Thank you, Michael. Awesome. Appreciate the feedback. All right. So everyone seems to be okay. So let's go to actually a page of the book. So I'm going to change my share here with you. And I'm going to go to a page of the book. Awesome. Now let's take a look at some of these. The earlier ones, pretty trivial. The row vectors, column vectors, you just identify those. Let's take a look at, for instance, like number 8. Let's take a look at number 8. Okay. In exercise number 8, let me get my notepad ready here. So we are in section 4.6, and I'm looking at exercise number 8 again. I'll try to do one similar to your homework problems. So here the matrix is 2, 5, 8, -3, 10, -7, 1, 6, 5. And the question, find a basis for the row space and the rank of the matrix. Okay. To find a basis for the row space. So that means we have to, what you call it, for the row space. So I need to get the matrix in its row echelon form, right? Let me change my share to my notepad here. There you go. Share it. Okay. So for the first part, I'm going to do Gauss-Jordan on this matrix. Okay. Now the Gauss-Jordan of this again, you can follow along in Symbolab. This ends up being 1, 0, 0, 0, 1, 0, or you can confirm it later. 4/5, 1/5, 0. Okay. So we can determine the rank, right? What do you think the rank of this matrix is? The rank is? Any suggestions? Anyone? What is the rank of this matrix? It will be 2, wouldn't it? It's the number of non-zero rows. So the rank is 2. Okay. Now, what about the basis? A basis for the row space, you just look at the non-zero rows. So this is actually part B. Rank is 2 for part A. The basis is going to have 2 vectors in it. 1, 0, 4/5, comma, 0, 1, 1/5. And there you have it. And that's going to be the number 8, exercise number 8. Well, let's take a look at another one. Switching back to the book. And then let's try, let's try number Basis for a subspace. Let's do the basis for a subspace, like number 12. So I'm going to write number 12 down. In number 12, the subspace of the vector space S is going to be 4, 2, -1, 1, 2, -8, and 0, 1, 2. So it looks like a subspace in R3, right? Because there are 3 vectors, each have A, B, C's. Okay, so again, we want to find a basis for this set, for this subspace. Let me go back to my note. Okay, so to find the basis, we're going to form a matrix A here, right? This matrix A is going to be made up of these vectors. This is like vector 1, vector 2, to vector 3. So we're just going to have the first row. The first row is going to be 4, 2, -1. The second row is going to be 1, 2, -8. The third is going to be 0, 1, 2. Okay. And then we're going to go Gauss-Jordan on this matrix. When we do Gauss-Jordan, this matrix is going to be matrix B now, we're going to call it. The row equivalent, 0, 1, 0, 0, 0, 1. That's what I got. So these are going to be the 3 vectors, W1, 2, and 3 that we need, right? So W1, the first vector, 1, 0, 0, the first row. W2 is going to be 0, 1, 0. And W sub 3 will be the third row, 0, 0, 1. There we have that one. Okay. Begin. Any questions? Anyone? If not, let's take a look at another one. Let's see. How about find a basis for the subspace R4? This is kind of like number 12. It's just instead of R3, you have R4. So it's the same process. Let's do maybe number, I don't know, we can do, how about number 20, let's do number 22. Okay, so I'm going to write number 22. In number 22, it says find the basis for the column space in number 22. A basis for the column space. 4, 6, 2, 20, -5, -11, 31, -6, -16. So that's matrix A. And then the rank of the matrix also. Okay. Now, to find the basis for the column space, remember we can do one of 2 ways. One is to find, the question says find the column space, right? We can actually find a row space for the transpose, right? The row space of a transpose is going to be the same as the column space of, what you call it? Column space of A. This is A. We want a basis for the column space. So just to be different on this one, I'm going to write A transpose. So the row becomes column. First row becomes first column. That's the transpose of the first row. The second row becomes second column of the transpose. 6, -5, -6, right? 6, -5, -6, 6, -5, -6. And the third row becomes third column of the transpose. That's 2, -11, -16. And then on this one, I did Gauss-Jordan. Remember, you can do Gauss-Jordan or the book just does row echelon form. Either works. You get different bases if you do that. But the bases are not unique anyway. So if I do Gauss-Jordan on this one, I got 1, 0, 0, 0, 1, 0, and -2/5, 3/5, and 0. Okay. So remember, this is the transpose. So the basis for the row space of A transpose are the rows, right? The non-zero rows. These will be basis for A transpose. So basis for column space is when you transpose the rows become columns. So it's going to become 1, 0, -2/5, comma, 0, 1, 3/5. You have to transpose these. And there you go. So this is for, now, this is column space for what you call it, for the equivalent matrix, right? This is matrix B. This is column space, basis for column space of B is, we want to find the basis for column space of A, right? So a basis for column space of A therefore consists of columns 1 and 2, right? It would be columns 1 and 2. So this is, right, first column, second column. It's going to be columns 1 and 2 of the original matrix. So this is the answer to the exercise, in other words. First column, 4, 6, 2. And the second column is 20, -5, 11. This is the answer. Okay. And yeah. And I think that's all it asked for. Okay. If we want, so what does this mean again? That means this third column, 31, -6, 16, -16, could be written as a linear combination of these two, that third column. Now, what is the rank? The rank of matrix A is the number of independent rows, the ones that don't have all zeros. It's going to be 2, right? Rank of A is 2. Okay, then there you have that one. Let me, again, any questions, anyone? If no questions, let's take a look at maybe one more. There's so many of these. Whoa. Let me see which one. Let's try exercise number 40 actually here. Something about the basis and dimension. So in exercise number 40, the question reads, find the basis for, and in part B, the dimension of the solution space of the homogeneous system of linear equations. Number 40. So I'll write this exercise, this problem. Number 40. So in number 40, let me switch back to my notepad. This one. Okay, so in number 40, the system is 4x negative y plus 2z equals 0. Then we have 2x plus 3y minus z equals 0. It's a homogeneous system, right? So it's all going to be 0 on the right side, equal to 0, plus z equals 0. Okay. Now, to find the basis, again, when you do Gauss-Jordan on this one, in number 40, I did, your Gauss-Jordan is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So this would imply that AX equals 0 has only trivial solutions. Okay. Now, it has 3 independent rows, right? Therefore, the basis for this is going to be X is 1, Y is 1, trivial solution, sorry. X equal Y equals Z equals 0. That's the solution. So the basis is going to be 0, 0, 0, because there's your X, Y, and Z. And what is the rank? The rank of the matrix is going to be 1, 2, 3. This is a full rank matrix. In part B, it says the nullity. So the dimension of solution space, right? Dimension of solution space, which it's called nullity or the kernel of that. The nullity is simply number of variables minus rank of A. Number of variables, 1, 2, 3. Rank is 3. Nullity 0. You see that? Nullity 0 means the system has only trivial solutions. Okay. And I think, let me see. That's probably enough for this one. I want to see if, shoot. Okay, so there's probably enough exercises we've done in this section. Good, we still have a little bit of time. So again, if there are any questions, please ask. Otherwise, I'll go on to the next section. So let's actually go to our next. Now we're going to skip section 4.7, by the way, and we're going to go to section 4.8. 4.8, we're looking at applications here. There we go. Applications of vector spaces. Okay. Now, this is pretty cool. If you already are taking differential equation, so this should be familiar to you. If not, this is kind of what awaits you for the future courses. So first of all, a linear differential equations. So this is from calculus. This is a linear differential equation. A differential equation is an equation that's made up of differentials. Okay. Now, the order of the differential equation is the highest, in fact, the highest, think of it as the derivative, order of derivative in that equation. So y superscript n in parentheses, that means the nth derivative. Y superscript n minus 1, this is the n minus 1 derivative. Y prime, we know that means just the first derivative, and of course y, no derivative. So this is the n order n differential equation, linear, and the linear part is, are these in front, those are linear. Okay, these are functions of x with a common domain. Now, if f of x equals 0, if everything on the left equals 0, then the equation is called homogeneous. Okay, otherwise it's not. Now, what is the solution? A solution to any differential equation, it's going to be a function, which they call it y. Okay, so the solution to this differential equation is an equation, a function y, that satisfies this equation, so that you take its first derivative, second, third, and so on, and then you work this out, it equals to f of x. Okay, so here's an example that he gives you. He says, what you call it? So suppose we have, this is the differential equation, simple, y double prime minus y zero. And he's already solved this. He says, show that both of these are solutions. So you have to take y is the original, so e to the x right here. That's that one. Y double prime, that's the second derivative of e to the x. Well, all derivatives of e to the x, all orders are e to the x. So e to the x minus e to the x equals 0. So it works. Okay, now what are we doing this for? There you go. Now, the solution of linear homogeneous differential equations is it has n linearly independent solutions, and the solutions are in this form. There you go. The solution is of the form C1y1, C2y2, Cn yn. Okay. And so that's just the solution. Now, how we find these remains to be seen, right? The y1, y2, yn. And then let's talk about the Wronskian. So this is what actually applies to what we're doing here. The Wronskian of a set of functions, y1 to yn, each of which has n minus 1 derivatives, is simply the determinant of this matrix of y1. Remember, y1 is a solution. y1, y2, yn are a set of functions that are solutions. So it's determinant of the first row, y1, first column, and then the first derivative of y1, second, third, all the way to the n minus 1 derivative. And then the same thing for y2, all the way up to yn. That's called the Wronskian. Okay, so Wronskian is a determinant. That's all that is. Okay, so how do you find the Wronskian? Here he has a set, right? This is the solution set, let's say. So here's y1, the first derivative, second derivative. Here's y2. Below it, first derivative, derivative of x is 1, second derivative, derivative of 1 is 0, and so on. Now this determinant is 0. Okay. Now, notice in part B, the Wronskian, the determinant is not 0, it's 2x cubed. Okay. So here's test for linear independence of the solutions. We want to know if the solutions are independent or not. So using the Wronskian test, suppose we have a set of solutions to the differential equation. The set is linearly independent, means these equations do not duplicate each other, or you cannot write one as a linear combination of the other one. If and only the Wronskian is not equal to 0, the determinant isn't 0. Okay, so there you go. That's the takeaway from this exercise. For us, this is what we need to do because we're talking about linearly independence. Now, let's take a look at just one example here. Okay, that's all there is in here, by the way. Don't worry about the other examples. So to do this, I'm going to actually go all the way to exercise number 22, the one that deals with Wronskian. We can skip the first 12 problems. So let's take a look at number 22. Okay, I'm going to write number 22 here. This is section 4.8 now. 4.8, number 22. In number 22, we have a set of solutions. I'm going to write like y1, y2, y3 is equal to, the solution is x, e to negative x, and e to the x. So suppose this is the solution to some differential equation. Okay, now let me change back to my notepad. Okay, so there you go. I wrote this exercise. And let's find the Wronskian. Okay, W is the Wronskian here. Remember, the Wronskian is going to be the determinant in this case of a 3 by 3. Starts with y1. And y1 is x. Our number 22. Did I write the problem right? Hold on, sorry folks, let me quickly look here. I said 22 and I wrote number 20. Okay, we could do 20, but 22 is better. Let me actually do number 22. Let me rewrite it. So it's x squared, e to the x squared, and x squared e to the x. Okay, so that's actually what number 22 is. All right, and you can still see my notepad. Perfect. Now, let's see. So let's actually do this. My Wronskian is going to be what? You're going to start with y1, that's x squared. Then you take the next derivative, that's 2x. The second derivative of 2x is 2. Now, then you go to the next solution, e to the x squared. The derivative of e to the x squared is itself, right, times chain rule. The derivative of x squared is 2x. Now, the derivative of 2x e to the x squared, we got to use the product rule of derivatives, right? Fg prime is f prime g plus g prime f. We got to use the product rule here. When we use the product rule, this is what you should get. I got 2e to the x squared, excuse me, plus 4x squared e to the x squared. And the last one, the last part is the last solution, which is x squared e to the x. The derivative of this using the product rule is going to be 2x e to the x plus x squared e to the x. The next derivative is derivative of this. And this derivative, when I did simplify it, you can verify these. I got 2e to the x plus 4x e to the x plus, sorry, I'm running out of room here, x squared e to the x. And then we have the determinant here. Okay, here, we're finding that determinant. And for this one, the determinant, now, I actually found this determinant using Symbolab. And I got negative 2 x squared e to the x squared plus x times 2x to the fourth negative x cubed negative 3x squared plus x plus 3. There you have it. So that's going to be the Wronskian. Okay. And all we really want to do for this one is the Wronskian. That's the determinant. Okay. And in just one exercise is all I wanted you to see as an application here, just to see how this works in context of the differential equations. All right, let me stop recording here